Hello and welcome to my presentation. My name is Rolf Westerteiger and today I will present you the new Geodict AI module which is part of Geodict 2021. This module allows you to train totally custom neural networks in order to solve your segmentation problems on 3D scans. As for myself, in 2008 I finished my diploma thesis at the Technical University in Kaiserslautern working on biomedical image segmentation. In 2014, I finished my PhD in computer science with the Technical University of Kaiserslautern and the German Aerospace Center in Braunschweig, working on virtual reality methods for the geosciences. Since 2014, I'm a full-time senior software developer at Math2Market, and some of the core topics that I work on are machine learning, the GeoPython integration, as well as structure generators. As for the agenda of my talk, in the first part I will give you a quick overview of Geodict AI and I will show you a sample scan that we want to segment. In the second part I will show you how you can train your own custom neural network using Geodict AI with the goal of segmenting this scan. In the third part I will show you some approaches and best practices in order to validate the performance of the trained neural network. And finally, in the fourth part we will apply the trained neural network to the scan that I've introduced in part 1. As you might know, since Geodict 2019, we are including FiberFind AI and BinderFind AI. Those come with pre-trained models for fiber and binder identification respectively. However, those models can fail for materials which are too different from the material models we had assumed when we did the training for these networks. For example, if the fiber diameters that you're analyzing are too small or too large, or if fibers have a non-circular fiber cross-section, etc., then these models might fail to correctly identify your fibers. In Geodict 2021, we now ship Geodict AI. This allows you to easily generate large amounts of training data in a short time by using the structure generation capabilities of Geodict. It then allows you to train a semantic segmentation network, and it allows you to apply the trained model to your real material scans. Note that efficient training requires a GPU, but consumer models are usually fully okay. So for example, you can go with a model for $500. As an example application, we're going to be looking at this scan of an NMC battery cathode. An NMC battery cathode consists of particles of lithium, nickel, manganese, cobalt oxide, which are held together by a binder material which is infused with conductive carbon black. They are difficult to segment by gray value alone. So we are looking at a binarized scan where we cannot distinguish the grains and the binder because they are both in the material phase. However, as we will see, the grains and the binder have characteristic shapes, and we can now train a neural network in order to distinguish the grains and the binder by their shape. But before we dive into this application example, let me give you a rundown about how Geodict AI works. Geodict AI learns to label voxels in a segmented binary image. Namely, giving a binary image such as the input image on the left-hand side, which has only the void material or background material and the material phase. It learns to mark or label some of these voxels, which then results in the output image on the right-hand side, where the marked voxels are shown in gray. In order to run the training process, we need several of these pairs of input and output images which correspond to each other. Namely, they have the same structure, but in the output image, the actual binder content is marked. Now the problem is, of course, that for our actual material, namely the battery NMC cathode, we do not know where the binder is, so we do not have the output image. We only have the input image, which has the grains and the binder encoded in the same color. But what we can do is we can leverage the vast structure generation capabilities of Geodict to create many synthetic material models for which, of course, we know where the binder is because the binder is being synthetically generated by Geodict and can be generated in a different color. And once this neural network is trained, we can then apply it to real scans for which we don't know the output. The first step in creating our neural network is creating a so-called digital twin. A digital twin is a synthetic microstructure which has similar statistic properties to the material we want to analyze. And of course, we can use Geodict structure generator to produce such a microstructure. Namely, we can use GrainGeo to generate the grains, as you can see in the first picture. and we can use process geo add binder to add the binder material between the grains. And as I mentioned earlier, of course, at this point, Geodict knows how to distinguish the grains and the binder because they have been marked in a different color. Now, in order to generate our training data set, we go and save the second image as output.gdt. Then we reassign the binder material to red. So basically we anonymize the binder so that it's not distinguishable from the grain face anymore. And we save that resulting image 3 as input.gdt. And during this process, of course, this final image input.gdt has to look as much as possible as the real material scan. And we can use the analysis modules such as Porodict and MudDict to verify this by measuring, for example, porosity and comparing it with the original material. Now we have manually created a pair of input and output structures which could theoretically be used for training. However, in our experience, it is better to have a few more structures of this size, 256 cubed. So we would aim for about, say, 10 structures. We could do this manually, but I want to show you how you can automate this with the help of Geodict AI. In the first step, we would create a macro from the steps that we just performed. For this purpose, we go to the session macro dialog, which is the dialog that is shown on this slide. And there we can see all the steps that were performed during our actions. From this command list, we only need to select the grain geo create, which was the grain geo structure generation, the process geo add binder, which added the binder, the save file operation, which saved the output GDT, the reassign operation, which recolored the gray binder to be red, and the last save file operation, which saved the input GDT. We pick all these by control clicking and selecting add selected commands to file, and then we can use the save button to save it as a GeoPython macro. Now the problem with this is because the grain geo create encodes the actual random seed that was used during the structure generation. If we replay this macro that we just recorded, we would always end up with the same structure. So to avoid this and actually introduce variation in our training data, we need to introduce one variable in our macro, namely the variable gd_seed of an integer type. This variable will assume different values when Geodict AI automatically generates the training data for us later. Also, we need to take this variable and we need to insert it in the random seed parameter for the grain geo create, so that grain geo actually generates different structures. Note here that this gdSeed variable can also be used to vary other parameters. For example, you could change the grain size distribution or the grain orientation or the amount of binder, but this is not covered here. In this case, the only thing that will change is the stochastic instance of the grain geo structure that we get. Now at this point we've created a macro with a single gdSeed parameter, and for each different value of gdSeed, this macro will produce a different pair of input GDT and output GDT structures on disk. And this is all we need to run the automatic training data creation in Geodict AI. So we go to Geodict AI, select Create Training Data and Edit, and we see the dialog above. In this dialog we specify the script that we have just created, we give an output directory to put the training data, and we give a number of structures for training and the number of structures for validation. Now the number of structures for training, those are the structures which will actually be used by the neural network during the training phase. So the network will look at these structures and try to optimize the segmentation process for these. And the validation structures are never considered during the automatic training phase. So these are mostly for manual validation afterwards. So the neural network training doesn't touch these, and you can look at them and validate the segmentation performance on these manually later. Now if we click OK, followed by Run, it will run the macro, in this case 13 times, in order to generate all these structures and put them in the appropriate subfolders. Now that we have the training data in place, we can finally train our neural network. For this, we go to Geodict AI, Train Neural Network, select Edit, and we get the dialog in the upper left corner. Here we can specify the result file name, which is basically the name of the subfolder where our network will end up. And we can select an input data folder, which in our case is the training data that we have just generated. And this is already enough to start the training. Let me note that there are several other parameters to set, but in this case we use defaults for all of them. One parameter that you might need to change is the window size, which as you can see here is 52 by 52 by 52. And this is basically the size of the input window that the neural network considers when producing its output. If your structures in your geometry are much larger than this, you might find that you need to increase this window size. There's also a maximum number of epochs that can be set towards the bottom of the dialog. A single epoch is one pass over the input data, so basically these are like iterations in a flow solver. So the 1000 we have here means that we do 1000 passes over the input data. But this is chosen very conservatively, and we usually never leave it running to 1000 epochs. Instead, if we click OK now and click Run, we can see on the right-hand side that we will be greeted with a convergence plot. And what we did in this case is just having the network run over one night. And we can see that the convergence plot has already plateaued. So we can assume, judging from the curve that we are seeing, that there's no further improvement going to be happening. So at this point we can click the stop button and we end up with a trained neural network. Now that we have trained our neural network, we need to think about how we can validate its segmentation performance. There are basically three levels of validation that you can do. In the first step, you can perform the validation on the training structures. As I mentioned earlier, the network saw these training structures and it was actively optimized on these training structures during the training. So this should usually be the easiest task for the network. In the second step, you can do the validation on the actual validation structures, which as I also said earlier, are generated stochastically from the same source as the training structures, but the network has never seen those during training. So there are different stochastic instances of these structures. So they are similar, but still it requires generalization. For example, one extreme error case that you could have is that the neural network basically memorizes all the training structures and memorizes the result. Then it would perform maybe perfectly on the training structures, but it would still fail on the validation structures. And finally, of course, you want to validate the performance of the network on the real material. And this usually needs even more generalization because it needs to bridge the remaining gap between the digital twin and the real material. Now in validation there are two types of errors that can occur. A voxel can be marked as binder where it shouldn't be, that would be a false positive, or a voxel cannot be labeled as binder where it should be labeled as binder, which is a false negative. What we can do for our synthetic structures, namely the train and validate structures, we can compare the ground truth, namely the output GDT file, with the prediction. Whereas the prediction, of course, is the application of the trained neural network to the input GDT file. And then we can indicate errors using color coding, as we will see on the next slide. Now here you can see a pseudo-SEM view of one training structure and one validation structure. I've chosen the following color coding. I've chosen dark red for those voxels which are part of a grain which have been correctly classified as a grain. And I've chosen a dark blue for binder voxels which have been correctly classified as binder material. I've chosen a bright red for such grain voxels which have been falsely classified as binder, and I've chosen a bright blue for binder voxels which have been falsely classified as grain. And you can see that most of the remaining errors are close to the interfaces between grains and binder. So basically you can interpret this as the neural network not knowing exactly where to put the interfaces. But still, if we look at the error table in the lower right corner, we see that the error is relatively low. All these error percentages are given as a fraction of the solid material, so the background is excluded here. And we can see that the error is below 1% in all categories, and curiously, the error is even lower for the validation structure than it is for the training structure. This could be due to regularization effects in the neural network training or just by chance. Now that we are fairly confident that the network works well on our training and validation structures, we can finally apply it to our real material. On the left-hand side, you can again see the binarized scan of the NMC cathode, where the grains and the binder are not distinguished. And on the right hand side you can see the end result that you get when you apply the trained neural network to that image. And you can see that the neural network delivers a plausible segmentation of the binder phase marked in gray. And by this we can tell that the network has generalized from our synthetic structures to the real material. Now on the left hand side we can again see the result in a 3D view this time, and we can see that the network has delivered a plausible binder segmentation even for difficult situations such as the 4 grains touching towards the upper right corner of that left hand image. And of course what this enables us to do is now we can subtract the binder from the image, which is now trivial to do because there are 2 different material phases, and we end up with isolated grains which can then easily be analyzed, for example using GrainFind or the other analysis modules in Geodict. And we can even go and use these metrics that we obtain with the analysis modules and use them to refine our training data. For example, we can use the found binder volume fraction in the left hand image and see if it differs from the assumption that we made when we created the training data, and possibly adjust the generated binder amount and retrain the neural network. As I said, this result was achieved with a training phase of only 1 night, so you can do a lot of experiments. In conclusion, I've demonstrated how you can use the new Geodict AI module in Geodict 2021 to train your own custom neural network-based segmentation models. And I've shown how by using the structure generators in Geodict you can totally avoid the problem that often plagues machine learning-based segmentation approaches, namely the lack of labeled data, because manual labeling is expensive and time-consuming, especially in 3D. But with Geodict you can generate an arbitrary amount of synthetic training data, so you don't have that problem at all. And even though the presentation was somewhat technical, I hope I've also demonstrated that Geodict AI is not difficult to use. The only thing you need is a Geodict digital twin, which is reasonably close to real material, and you have to create a macro. And then Geodict AI can automatically generate the training data for you, run the training, and finally apply the network to your actual materials. And here I want to note that if you do not want to do these steps by yourself, we can also always offer projects where we either model your material or create a neural network directly for you, or both. Considering future work regarding machine learning at Math4Market, one thing we want to explore is finding generator parameters automatically to match a given material. For example, in this case, to find the grain geo parameters and find the process geo add binder parameters, which most closely resemble the real material. If we get to this point, then basically this whole process could be automated. With this, I want to conclude, and I'll be ready to take your questions.